Alrighty, we are getting ready to get started. So last call for the QR code. Okay. Good evening, everyone. Nice. Thank you so much for coming out today. Today, we will be presenting Space City Rocketry's preliminary design review for the 2022 through 2023 academic year. First item on our agenda is the team introduction. We will follow up with an overview of our rocket, Shasta 6. This year's rocket was named after our school's mascot, whom recently passed away. Next, we will cover what analysis and propulsion have worked on throughout the semester. After that, Structures would like to present what they have planned for this year. The payload subteam has been working extremely hard this semester, and they have their experiment decided and ready to present. Recovery will introduce their plan to recover Shasta 6 in flight-capable conditions. Lastly, we will conclude our presentation with the avionics subteam. So, team introduction. Space City Rocketry is one of two competitive engineering teams under AIAA. So what's so unique about this year? Well, as of October 22nd, we have a total of roughly 80 members. Every sub-team has 2 co-leads this year. The reason why we did that was because this is something brand new that we are trying out this year. We wanted the workload for each sub-team to be divided evenly, in case one of the leads need to focus on academics or personal matters. So we wanted to ensure that nothing would get in the way of our success of getting Shasta 6 built. The payload and avionics subteam has a collaborative group coined as Pavionics. We wanted a more collaborative effort between the payload and avionics subteam. Both subteam leads encourage this process and organize collaborative lab times. We also have new bay designs for payload and avionics, as well as a tray redesign. And lastly, we have the most female members in SCR history. So now I will have Robbie present the primary mission.
Hello, everyone. My name is Ravi Desai. I'm a senior majoring in mechanical engineering here at the University of Houston, and I'm Space City Rocketry's chief engineer for the 2022-2023 year. I'll be covering our primary missions briefly. Of course, we are designing and building a solid propellant 30K COTS rocket to compete at the Spaceport America Cup in 2023 in Las Cruces, New Mexico. We are placing a special emphasis this year on SRAD components in hopeful preparation for a 10K SRAD rocket in the coming years of SCR. Specifically, we'd like to place in the top 25% overall and the top 5 in the 30K COTS category at Spaceport America Cup. Some of our other primary goals are to have a fully completed working design by the end of the fall semester, which is possible thanks to everyone attending today and providing your feedback. Sorry about that. We are also focusing on manufacturing, assembling, and testing in the spring semester. In the past with Space City Rocketry, we've struggled to adhere to a strict timeline with a lot of our design and manufacturing work. So this year we're hoping to make that a much smoother process and allow us to spend more time on manufacturing, assembling, and testing. We'd also like to host more social events in collaboration with AIAA U of H, and of course, deepen members' engineering knowledge and set them up for that real-world success. Some of our secondary missions include beginning research and development into SRAD solid rocket motors, encouraging members once again to obtain their L1 flight certifications, continuing the research and development of composite tubing using the X-Winder with our structures subteam, and mainly with our analysis subteam, continuing the practical use and learning of various engineering simulation software, such as CAD, FEA, CFD, and also getting our feet wet with some custom flight simulations. Joe will now cover our team structure for the upcoming year.
Thank you. So, as you can see in front of you, Randy Mark is our EEE flyer of record. Dr. Sescon is our UH faculty advisor. Space City Rocketry falls underneath the AIAA branch, where I, Josephine Arguello, the project manager for this year, am working alongside Ravi Desai, chief engineer, who you just met. We have one lead for analysis, Omar, the avionics leads, Raj and Samantha, which you will be meeting shortly, the payload leads, Isabel and Kevin, propulsion leads, Scott and Parsa. Next, we have the recovery leads, Christian and Bailey. And lastly, the structures leads, Brandon and Ali. Okay, so team demographics. As you can see, what we can conclude from our demographics of this year is the following. Our team is mainly comprised of sophomores, as you can see from the huge 38% in our diagram. We have the biggest percentage of women on the team in all of SCR history. And then lastly, the most common race and or ethnicity on the team is Hispanic/Latinx. We even have an international student this year from Mexico who decided to join the avionics sub-team. We will now continue our presentation with a general overview of our rocket Shasta 6. So our goals. What are our goals and what do we hope to gain from this? We hope to receive feedback from alumni, mentors, and professors, demonstrate our competency of design to move forward in our design process, and to demonstrate an elimination of risk to a degree. So this year we came up with a brand new risk matrix diagram, which we are excited to show you guys.
So the current status of Shasta 6 to this point, we are roughly 35% complete with our entire project. This is assuming that 50% is the end of the fall semester and 100% is at launch at Spaceport America Cup. We plan to have all items purchased by the end of November. And over the next month, we'll make a lot of sincere efforts to make any changes, any major design feedback that we get from all of you guys for our CDR and obviously during the PDR. Now, a brief discussion about Shasta's rocket diameter. We will be going forward with a 4-inch or a minimum diameter rocket. This means that the airframe of Shasta will slide right over the motor that we will be using this year. We reached this decision through trade studies conducted by every sub-team and the project leads. Although we found that 6 inches may be more ideal for recovery, avionics, and payload, due to giving them some more space for components and experimentation that we'd like to see, we decided that moving forward with 4 inches would be ideal for actually reaching 30,000 feet this year and consequently improving our placement at Spaceport. We believe that not enough changes could be made to a 6-inch diameter rocket to allow us to reach 30,000 feet in apogee, and we felt more comfortable moving forward with the 4-inch design for this reason. A brief note about the timeline so far. In the beginning, we had our budget determined with Arturo, the AIAA U of H treasurer, and we'll be getting to that in the next coming slides. Our rocket diameter decision was our first major task, as that kind of sets the tone as to what every sub-team can accomplish. Over the past 2 months, we've obviously been working on getting all of the tasks that we'd like to see completed for the preliminary design review. We've had our Shasta preliminary design and component layout complete, which Omar will be covering with analysis. We spent about a week doing some in-class recruitment in collaboration with AIAA, and spent around just over a week conducting interviews for new members onto the team, and then finally admitting them. And today is our preliminary design review. Now, moving forward, these dates are a little rough, but we do know that we obviously would like to redesign based on the PDR feedback. We want to finalize our bill of materials in our budget, and we want to finalize Shasta 6 design and component layout, and pretty much where all of our systems are placed, and have a full working design by our critical design review, which will be November 18th. After our critical design review, we would like to order all COTS components to enable us to start manufacturing into the spring semester.
All righty. So we currently have around $3,500 in our account. Ideally, we need roughly around $11,000 to $12,000 if we would like to attend Spaceport this year. We have raised around $1,500 so far through our efforts of donation by alumni and bake sales. We will continue to fundraise through donations, bake sales, and sponsorships. We have a bake sale coming up next week, which is Wednesday, October 26th. And then also huge thank you to Dominic for donating some of his money to different SRAD projects this year. If you are interested in becoming a sponsor or would like to donate to our cause, please reach out to aiaacougs.uh@gmail.com, or you can speak to either myself or Robbie after this presentation. Okay, up next, we have the sub-team projects. We will start off with the analysis sub-team lead, Omar.
Great, thank you. So my name's Omar. For those of you guys who don't know, I'll be going over what analysis does and what we've accomplished so far. I'll try to keep this as concise as I can. So what is analysis and what's our purpose? Our main purpose is to, one, design the layout of Shasta, kind of take responsibility of that. And also design the layout of Shasta, as well as provide design validation for those decisions. In addition, we'll also CAD any relevant components along the way. So the way we validate these decisions, I'll kind of go over a few examples in the subsequent slides. But one way is through hand calcs, FEA, CFD, which hopefully we'll do a little bit more as the design progresses. Besides that, we also focus a lot on flight simulation softwares. So this year we're actually using three, those being OpenRocket, RockSim, and ROS-Aero. Basically, we'll be able to predict how the rocket will perform in here. And the reason we're using three is because, one, we're not 100% confident which one we can trust the most. And given the fact that we unfortunately won't be able to have a test flight this year, most likely, we'll be heavily relying on these simulations. So a little overview of the scoring of Spaceport America and why we place such an emphasis on this. So out of the 1,000 points total possible, 500 of these come from flight performance. And then out of these 500, 350 come from how close we get to our target apogee, which in our case is 30,000 feet. There's a plus minus of 30,000 feet, of 30%. So if we do stay within the 21,000 to 39,000 range, we get points, but obviously the closer we get to 30,000, the more we get. So going into the design itself, our layout looks pretty similar to last year. Of course, the biggest difference being that we're 4 inches instead of 6 inches. Oh, sorry, I didn't see that. The material for the airframe, nose cone, and bays is going to stay being G12 fiberglass, and those are the respective dimensions for each component. Another noticeable difference is our bays, avionics, and payload are a little bit longer, just because they'll need a little bit more space, given the smaller diameter. And that's kind of what our layout looks like. We have a lower upper airframe, nose cone. Our payload bay serves as the coupler between the lower and upper airframe. And also, sorry, let me just get that down. And then our avionics bay lies in our upper airframe. Okay, so basically this table shows what each of our flight sim softwares have predicted. One major highlight is the apogee difference. There is a pretty significant difference in what each one predicts for how high we'll go. So through a little bit of research on our own, we compared our past flights to try to gauge, which one we can trust the most. That didn't really have a clear conclusion. We asked our mentor, we asked Spaceport, and through our own research, we're tending to lean more towards ROS-Aero and trusting that the most, just because it calculates drag the most accurately. One other note I want to add is we're overshooting a little bit, just because this is assuming that everything goes perfect throughout manufacturing, which most of the times it really doesn't. Okay. So for our nose cone, Our final decision is to do a 5-to-1 tangent ogive shape, which you can see in the top right. Basically, the way we determined this was we ran a bunch of different configurations on potential shapes that we wanted to look at, and looked at how much drag gets induced on the rocket based on each shape. So OpenRocket and RockSim showed that 3-to-1 tangent ogive was the best to go with in terms of drag. However, Ross Arrow said 7-to-1 von Karman, but the difference between these wasn't large at all. We did go a little bit longer. The reason we went 5-to-1 was to give recovery a little bit more space. So we weren't, just for 12 inches in length. Next, I'll talk about the fins. So the fin shape that we're going to go with so far is in the top right, sort of a trapezoidal shape, just a little bit swept back. The way we chose this was we wanted to maintain the 1.5 to 2 calibers of stability that Spaceport wants us to maintain. And then 2, we wanted to look into making sure that our fins don't flutter and divergence velocity isn't exceeded. Basically, those are events during flight that could either cause our fin to deform or rip off completely. To study that, we use a software called Aero Fin Sim. Basically, we looked at a few different configurations, kind of like the nose cone, and basically outputted at what velocity those events would occur, and we'll make sure not to exceed that during flight. So we have a factor of safety of 1.31 before divergence occurs, which is the first major event that would happen. One major difference is we're actually doing 3 fins this year instead of the typical 4, just because that gives us the most, leniency with stability if we want to change it down the line. They'll be made out of carbon fiber, and the thickness is going to be 6 millimeters or 0.236 inches. Some future plans that we want to do before the end of the year is find when max Q occurs. This is max dynamic pressure or mechanical stress on the rocket. We do want to make some progress on the custom flight sim software down the line. We also want to continue any relevant analysis throughout the year. One thing we were looking at is buckling. So, if you look in the table in the bottom right, we made a little plot of, just how much compressive stress or the max compressive stress that might happen throughout flight. Right now we're looking at 125 PSI. We're not sure how accurate that is. So if anybody has any feedback, if that sounds somewhat good, we would appreciate that. And of course, we'll continue to assist any other sub teams throughout the way. And like I said, any advice, tips, anything you guys can think of that we might have missed or overlooked, feel free to let us know. We'll definitely look into it.
Yes. So we have completely revamped the way we've been looking at risk for the past few years. If you've attended previous presentations of Space City Rocketry in the past, you would be familiar with the risk matrix, which was a nice, colorful little grid of risks that we would place into each box depending on their likelihood and consequences. This year, Ezra has released a risk assessment table, kind of template that they'd like to see be used by teams. This is going to include the failure mode or the event, or just the general risk that's possible, some of the possible causes of said risk, the risk of the mishap and your rationale behind defining that risk. Your mitigation type is going to be either risk that can be mitigated through design, risk that can be mitigated through procedure, or risk that cannot be mitigated and is out of our control. We'll then detail some of the mitigation approaches that we have taken or will take, and then our consequential risk after mitigation. So Omar will talk about some of the stuff the analysis subteam has been looking at so far, and every subteam will have their own edition of a risk assessment table to provide a comprehensive look at risk for Shasta the Sixth as a whole.
Thank you. So to go over our risk assessment, so we came up with 5 events that we thought could occur during flight that were relevant to analysis that could lead to its failure. First one is fin failure. Possible causes could be the fin isn't thick enough, the material is not strong enough, or the shape just makes it more prone to it happening. So before our mitigation, we classified it as extreme. However, afterwards, we classified it as just medium. So basically, we optimize it through design, made sure that the material would be strong enough, shape, etc. Our next would be buckling. So basically, this can happen if there's extreme compressive forces that occur during flight. Prior to mitigation, we classified this as high. However, after we classified this as medium, one way we'll mitigate this is minimizing the amount of empty space within the airframe so that there's either a bay or a motor casing also supporting the airframe and not just it itself. Next, we'll do bay fastener failure. So basically any screws or bolts that are in the bays that are holding it in place that might shear. Prior to mitigation, we classified this as high. Afterwards, it was medium. Basically, we used the screw calculator from last year, which we trust, just because none of the screws from last year sheared. And then motor retention fastener failure is pretty similar to bay. The only difference is that we classified it as extreme before mitigation, but afterwards it was also medium. And then finally, an unstable rocket flight. This could occur if the rocket's overstable or understable. This can be an extreme risk prior to mitigation. However, afterwards, we classified this as medium. Since we'll be using 3 different flight sim softwares, we trust that it'll be stable throughout flight. And then this is just a timeline of what we have left. Basically redesigning, like Ravi said, determining any testing, risk mitigation, doing our final layout, researching any buckling effects, and then our CDR, of course. Thank you.
We'll now have Parsa and Scott come up and talk about propulsion.
Hello, everyone. I'm Parsa and this is Scott. We're the 2 co-leads for propulsion this year. So we'll just get right into it. So for this year, we'll be reusing last year's motor, the Cestroni 03400. So some quick facts about this motor. Has a total impulse of 21,000 Newton seconds, a maximum thrust of 4,750 Newtons, an average thrust of 3,416 Newtons, and a burn time of 6.16 seconds. So like, we were using it, but why? So we'll be reusing it, one, because this reduces the team's expenses. Pretty expensive just go buy another motor. And already the reload costs around $1,600. The team also has prior experience with this motor. This reduces risk of misassembly at spaceport. And this motor does provide sufficient impulse to reach our goal of 30,000 feet. And if we want to compare it to like a motor from last year, which was its main competitor, the N5800, the 03400 has a similar total impulse and double the burn time. So this reduces the acceleration on of the rocket and reduces the forces on the body frame. So our current status is we have inspected the 03400 and cleaned it up. It does have some scratches and minor scuffing on threads, and there's some residue left over near the nozzle, but we do think it is ready to be reused for the next competition. And all we need to really do is just buy another reload kit.
All right, hello, my name is Scott. I'm going to go over the risk assessment. So some of the risks we're looking at are starting with ignition failure. So that could happen because we input the igniter in wrong, perhaps, or prepared it improperly. It's pretty low risk because it's not really dangerous to the personnel or the flight. It might have to, just through procedure, which would be our mitigation. We'll just follow the right procedures and obey the launch control officer's instructions. And overall, it's a pretty low risk thing. One major thing that could go wrong is just that the motor explodes. And this could happen because propellant clogs the nozzle due to fuel grains coming loose, or if the motor casing was damaged from the last flight. So this is improbable, but pretty catastrophic. So we put it medium risk. It's pretty rare, but it can cause some damage and possibly hurt someone. So through procedure, we will just make a thorough inspection of the parts and make sure the grains are all good when we're putting it together, and maintain a safe distance from the rocket. Overall, pretty low risk. I mean, it's accepted. Everyone goes and launches rockets, but they can't explode. So premature ignition is another hazard, and that could happen due to improper wiring of the igniter, accidentally contacting live circuit, maybe in the avionics bay or something like that. Pretty improbable, but it would be catastrophic because there's a risk of someone getting injured while that happens. So through procedure, we will just handle equipment responsibly and obey the launch control officer's instructions. and that is also low risk. And then improper assembly of motor is pretty similar to the catastrophic destruction earlier. This is a little more focused on the rocket, and we would lose the rocket, and it would not be reflyable if it were to explode, and we'd lose a lot of points on that. But yeah, through procedure, same thing, make sure we put it together properly, make sure it's all inspected. We have experience from last year on putting it together, so that's overall pretty low risk thing. And our budget is around $1,900 for the reload, as well as the hazmat shipping fee, because it has to be transported safely.
So for our timeline, before the CDR, we're going to finalize the risk mitigation and just finalize our budget. Since the motor has been decided already for the 2022-2023 competition, propulsion is going to be focusing more on SRAD motors. Our first goal right now is to get our members L1 certified, as many as we can, by at least 50%, so that we can start testing motors of higher impulses legally. Yeah, and then we also have our SRAD test stand we'll continue working on. We're also working with a capstone team on that. And yeah, that's it. Thank you.
We will now have Brandon come up to present structures.
Hello, everyone. My name is Brandon. I'm one of the co-leads for structures this year. So getting into an overview of structures, we are responsible for the designing, purchasing, or producing based on the component, and the assembly of these structural and aerodynamic components in our projects. We work very closely with analysis to get validation for these components and make sure that everything is to the strengths that we require for our rockets. Some of the main components that we have been working on for Shasta have been the nose cone and airframes, of course, being the 4-inch minimum diameter. The avionics and payload couplers, as well as the modular fin can, which have slightly new designs that we are kind of working towards. And of course, the motor retention system, which we are basing largely on Zenith's past design. Jumping into the coupler or bay, the new design steers away from the all-thread rod approach that we've seen in our previous designs. We are moving into a rail system. So as you can see on the right, that is the avionics configuration. And there are 4 rails positioned 90 degrees on the inside of the coupler that are made out of G10 fiberglass. Due to this system, any component that we put in these couplers can take any shape while meeting this rail requirement, as long as they attach to at least 2 of these rails, like you can see in that picture. This greatly increases the ease of assembly for these, as they can just be slid on and off the rails pretty quickly. We will have to kind of design spacers in between each of these trays, just so that they can be supported correctly during landing and in-flight forces. The main reason for this design going into payloads configuration was an increase in the inner volume and the utilizable space that they can use for their experiments. So with the previous all-thread rod design, the entire center of that bay would not really be usable, just because it would be filled with, fasteners and nuts and stuff. So hopefully this will give them a lot more freedom in terms of what they can design for their experiment. So more specifically, the payload coupler. So for fasteners, we are planning on using 6 832 alloy steel screws that would be secured radially around each of those bulkheads. So in the previous, actually, you can actually see it here on the very right side. You can see some of those bolts that would be going into that bulkhead. To complement this, we would have threaded inserts that would be placed inside of those bulkheads that would be epoxied in place. Because of this, our bulkheads are going to have to be thicker to account for the fasteners that we will be putting in there. So the previous thickness that we've used for our other couplers are 3/16 inch, and we'll be moving it to around 1/2 inch to make sure that we have enough material to support those screws. The experiment housing, which you can also see on that right side, is going to be secured through the rail system. It'll be slid on, but of course that wouldn't restrict it vertically. So we're also going to have some fasteners coming through the bulkhead or through the side of the couplers to make sure that we can support it throughout the flight. As far as avionics goes, we're taking a slightly different approach in how we are securing everything inside of the airframe. We'll be using, the current plan is we'll be using 4 832 alloy steel screws that will go perpendicular to the bulkhead rather than parallel or through the edges. This is mainly due to the decreased mass that we expect in the avionics bay versus the payload bay. But a problem that arises is due to this, I guess, configuration of the fasteners. The loading would be parallel to the direction of the screws rather than I guess, perpendicular. So rather than shearing the screws in failure, they would just be pulled apart. So with the threaded inserts that would be used with the alloy steel screws, we would have to epoxy those into the rails right below that bulkhead. And so we are expecting the alloy steel screws to take a majority of that load, and that that is what the number 4 of the screws has been based off of. But if the epoxy bonds between the rail and the threaded inserts were to fail before our screws, we would have a greatly reduced maximum strength. So I realize that calculations for epoxy bonds and just surface adhesion is pretty difficult to calculate based on the geometry of the surfaces that are being joined. So we are hoping to get into testing and kind of getting a physical, I guess, physical validation for this in the upcoming months. As you guys have seen in the previous slide and a little bit later on with avionics, the tray and components that will be placed inside of this bay can be pretty modular, and they can be very just very unique than what we're used to with the previous design. The motor retention system, as I mentioned earlier, is very similar to what we went for with Zenith. The main difference is that we are not planning on using aluminum for the structure that will be holding the motor up. Just due to costs of manufacturing, machining, materials and all of that. It'll be generally easier to work with G10 fiberglass because we can kind of do all of that in the lab, and we don't have to worry on third parties to kind of help us out. That being said, if we do have the opportunity to move in the direction of aluminum, I think we would rather do that. But in terms of just ease of assembly and manufacturing and costs, we are looking in the direction of fiberglass. The only expected load that will be placed on the motor block would be the weight of the motor. We're not expecting the motor block to support any of the thrust forces that occur from the motor being ignited and are sent. So we are going to a smaller diameter screw for securing this in place. Because of it only supporting the weight of the motor, we really don't need that many screws. So we're expecting anywhere from 4 to 6 just to be safe and just to, I guess, generally keep everything secured safely. But I don't think we would need that many screws just from the forces that we are expecting. And that being said, the thickness of that fiberglass bulkhead could also be changed based on what fasteners we are using and how many we are using. Moving on to the modular fin can, this has been a tough design process just because of the movement into the minimum diameter design. We can't really utilize any fin tab methods for securing the fins in place. So we realize that it's going to be pretty tough and pretty complex to manufacture this in a safe way. that we hope will survive a flight. So in order to keep this main assembly modular, or as modular as we can keep it, if you look at the bottom right, there is a photo of the current CAD for the fin geometry and fin can design. Right above the fins, there is a break in the airframe section. And so that lower portion will be completely removable from the rest of the airframe. So the fins will be mounted on that section of airframe, just surface mounted. And of course, that would be the carbon fiber plate, I believe 0.236 inches, if I remember correctly, or somewhere around there. But we'll be surface mounting those on there from the root cords, and then having a epoxy and chopped fiber fillet that will run along both edges of those fins. And additionally, we will have the carbon fiber tip-to-tip layup that you can see in the top right photo. That is from our work with Zenith, which we had a little bit of trouble with, but due to our experiences with the layup and that whole process, we're hoping that we can use that knowledge that we gained and kind of have a little bit better luck with this one. It is notable to say that we don't plan on securing the fin can to the motor casing or to the airframe. So it would technically be free to rotate if there's not enough forces between the motor and the airframe above it, kind of compressing it. In flight, due to the thrust forces of the motor, that would push up on the fin can assembly and into the airframe. So we don't expect the fin can to twist or rotate at all during the ascent. If it did, I don't believe that we would have any problems with that, because the only thing that it would really affect is the roll rate of the fin can, which wouldn't be affecting the entire rocket. So although we don't expect the fin can to rotate independently, it wouldn't be that much of an issue for the entire assembly. Another tough design point is rail buttons. So the internal reinforcement of the rail button hardware is not a possibility for this design, because we are again going with the minimum diameter design. The previous methods that we've used is an internal hardpoint that match the internal radius of the airframe that will just, I guess, apply pressure to the inside of the airframe, giving our rail button a little more strength. So to kind of get around this, we are thinking of surface mounting our hardware. So you can see the bottom weld nut that just has a large base that we can use to epoxy to our airframes. So we will be planning on surface mounting those, doing fillets around the edges, and then doing additional layups around that to strengthen that assembly. We have two options that we are thinking of that we'd like to get your input on. I guess I should mention first, again, we are planning on using fillets around each of these options. So in the space between the bottom of the rail button, which is the rectangular portion on the cross-sectional views that you see, and the bottom of the weld nut, there will be fillets that would be taking up that space. So for option one, it would be mounted about ½ an inch away from the airframe to give us room to do those fillets and to make sure that we have a very secure connection. Yeah, but it would increase the amount of drag that the rocket would feel, and due to the distance away from the airframe, it would have a higher chance of damage during landing or just during the launch procedure going off the rail. The second option would be a little more sleek. It would be flush to the airframe, or I guess the bottom of the rail button would be flush to the airframe. But we would want to still have fillets or layup over this to increase the strength. And so that would require us to kind of change the internal geometry of the rail button to kind of account for this. So you can see that there's a bottom chamfer that is inside of that hole on the cross-section view on the right side. And so that is where that fillet and layup would be housed. The addition of this would kind of create some geometry that isn't commercially available. So the rail buttons that we currently purchase are just Delrin plastic rail buttons that we purchased from Apogee Components. But in this second option, the change in geometry would require us to make our own. And so we are kind of looking into a resin molding process that would allow us to make these rail buttons and kind of set a future, I guess, basis for making our own components that have slightly complex geometry. So the top one, option 1, would be using a 1/4-20 bolt, and the second at the bottom would be using an 8/32 bolt. So with this process of resin molding, we would be able to decide the hardware that we could use, the geometry of the rail buttons, and everything like that. So we are just kind of balancing these two and trying to think if it's worth it to kind of go in the direction of the second option, creating a new procedure for molding and kind of changing that up. In the future, we are planning to test a lot of these components as they're fairly new for us in terms of the minimum diameter components. So we are reaching out to professors and alumni for advice, because at the moment I am not the most knowledgeable on the testing processes for materials and calculating the maximum strength and stuff like that. So we are relying a lot on outside input to kind of help us with the validation for that. Some of the components that we are planning to test are the fin can, so more specifically the fillets and layup process that would go into the fins. The main thing that I would like to kind of touch on with that is the addition of carbon fiber or fiberglass chop fibers that we would place into those fillets. Doing our research last year, we concluded that the addition of these fibers would increase the strength and just overall stiffness of the overall structure. But I would like to kind of get some numerical values and some more validation behind that so we can make sure that we are moving in the best direction possible. Just because going to Spaceport last year, we witnessed a lot of fin cans and fins breaking off mid-flight. It was not the most reassuring sight. So I'm hoping we can kind of avoid that. Next is rail buttons, as I mentioned earlier. So the hardware attachment, so mainly the surface mounting and fillets and layups that go with the smaller hardware of the rail buttons. Next is the bulkhead fastener strength for payload and avionics. So we want to make sure that the bulkheads can properly support the weight with this new design, and that the thickness of the bulkheads will be properly sized and won't kind of delaminate on themselves whenever a force is applied. And lastly, well, not lastly, but we've been working a lot with the X-Winder machine to make composite tubing, and that is actually the two pictures that we have up there. The one on the right is the most recent one that we've worked on. It looks pretty good, but we still have a lot of kind of way to go before we can, fully make our own airframes and couplers, stuff like that for our SCR rockets. Last would be vacuum bagging for composite layups. So Randy has talked to us a little bit about the benefits of using vacuum bagging for the layup process and kind of avoiding this regular hand layup process to make our components. So it is something that I want to look into, but it is slightly expensive and slightly complex for, I guess, the current components that we are looking at. So hopefully we can create a basis for that and start looking into it in terms of implementing that into the future rockets. For the risk assessment for structures, we mainly tried to focus on the things that would strictly affect structures and not necessarily go into the area of analysis. That being said, there is some overlap, so bear with me with some of these. The first is damage of aerodynamic surfaces, or just the general structures that would be on the outside of the rocket. This is a risk of medium due to just improper handling and accidental damage of the airframe, which could ultimately decrease our total apogee, just based on the amount of drag that the rocket would feel on the ascent. We would mitigate this through procedure and establishing handling procedures for transportation and assembly. Next would be motor block failure. So more specifically, this would be caused by fasteners or just incorrect assembly. Due to having a very similar design for this year's system as compared to Zenith's design, we hope to have some comfortability with that and mitigate that through the pre-flight checklists and just experience that we've gained from that system. Fin failure, of course, I touched on this earlier. This would be a very high risk, as if our fins were to fail due to fin flutter or due to just general aerodynamic forces, we could lose the entire rocket or possibly hurt some people that are in the competition. So this would be caused by misalignment or improper mounting of the fins during the initial process of manufacturing for the fin can, and imperfections in the composite fillets or layups that we do. We would approach this through design and procedure. A method that we kind of worked on last year was utilizing 3D printed guides that would help us with the proper alignment and surface adhesion of the fins to kind of help us in the later steps of filleting and layups. Next is tear out of the rail button hardware or just general failure. This would occur during the launch portion of the rocket while it's moving off of the rail. It has a risk of high just because, again, if we were to lose control of the rocket at this point, we don't exactly know the trajectory or the direction that it would travel, which could range from minor changes to our apogee or trajectory to a complete loss of the rocket. We would mitigate this through design and by, of course, choosing the proper options that we have laid out right now, and through the testing process for verifying that it can withstand the loads that we would like it to. Fastener and hardware failure. Again, these are high risks because we rely greatly on the screws that are holding together the entire assembly. Specifically with the couplers, avionics, and payload, if these were to fail during any point in the flight, we would lose the experimentation or the data that we were trying to gather for the rocket. But of course, if this were to happen to any of the other sections, maybe the coupling of the lower and upper airframes, that would of course be a lot greater of a consequence. We would mitigate this through design using the screw calculators that analysis has put together. We expect to have a safety factor of 2 for all of our load-bearing components. And an experience that we had last year at Spaceport was the epoxy failure for some of the fasteners that were inside of the payload bay. And that was due to the epoxy that we had used in securing those nuts inside of the bay. So this year we are making sure that we go through the material properties of the epoxy that we are planning on using for that, and making sure that it can expect the, like I said, it will work properly in the heat that we are expecting at Spaceport. And generally, from the data that we collected through the avionics system last year, that'll be around 100 to 120 degrees Fahrenheit. Last is the component failure and damage risk. So that would be caused from fractures or damage from transportation or test flights, if we do have any, or damage from the landing loads or dragging after the recovery process of Shasta. We would mitigate these through design and procedure based on which purpose it would come from. So for transportation and test flights, again, we would set proper handling procedures and making sure that we have materials that we can transport the rocket safely in. So it could be bubble wrap, it could be moving blankets, or just anything like that. As far as the landing loads or dragging, we will, of course, mitigate that through design and making sure that we have the expected strengths from each of the components that would be that we expect to take the bulk of the loads during these events. The budget for structures this year is $1,000. This is a general overview of the things that we expect to purchase. Of course, the airframes, the 5-foot and 4-foot section, the couplers for each of the payload and avionics subteams, the carbon fiber plate that we'll be using for our fins, fiberglass plate that we'll be using for the couplers, the bulkheads, sorry, for those couplers, and then screws, the nose cone, and we also included some materials that would be used for the resin molding techniques that I spoke about for the rail buttons. Of course, depending on which options we go with, that may or may not be included in our final budget. And the timeline for structures mainly depends on how quickly we can go through the testing procedures and final design processes for each of our components. But some of these things would include the finalization of the avionics and payload bay designs, which would include the bulkhead design for recovery and avionics, the motor attention methods, fin attachment, and fastener size and location, and the rail button decision based on the options that we have currently, risk mitigation, and the testing that we would like to complete in the spring. Lastly would just be the build materials we spoke on the last slide, going on the processes that we expect for the rail buttons and for the overall methods for composites. We'll change it up as we go.
Next, we'll have Kevin and Izzy talk about our payload experiment this year.
Hello, everybody. I'm Kevin, and this is Izzy, and we're the payload co-leads, and we'll get right into it.
Hi, everyone. So Payload got together late July this year to start coming up with and designing an innovative experiment that will give Shasta 6 a unique reason to launch. One thing we want to do as we follow through with entering the SDL Payload Challenge and hoping to be successful with it is use electronics to emphasize and elevate our experiment and data acquisition. We definitely want to collect and analyze applicable data. So Payload is split into 2 teams as we finalized our new rosters. Half of our new members went to the scientific execution side. That includes designing and executing our cooling enclosure, fly upkeep, documentation, stuff like that. And then our payload electronics or our pavionics will be doing their own PCB board with about 3 sensors for payload to give us numerical data throughout the flight and any backup data in case there were a crash. So they focus on our sensors and electronics, and then data collection and analysis will be shared between the 2 teams. So to provide a base for our experiment, we did some extensive research to give a background to all of our knowledge moving forward with our experiment. We have a very lengthy paper that we're working on throughout the year and we'll be updating and adding to. It's called our statement of work. So this can be found in there. One thing I would like to define is just the state that the flies will be in throughout the experiment. So we are hoping to achieve a homeostatic torpor state, which is a state of hibernation you can get through by lowering the temperature. They go into hypometabolism and hypoactivity. So they pretty much just go into like a lengthy sleep. Therapeutic hypothermia is not necessarily freezing them, but it is lowering their temperature. In cases of hibernating animals and also just like treatment on humans, therapeutic hypothermia's main purpose is preserving organ viability. It's also known as one of the strongest neuroprotectants, but with that being said, it's never been conducted or tried out on an organism in a high stress environment. Astronauts are definitely exposed to numerous health risks with every bodily system during space travel. We want an emphasis on the pressures of cardiovascular and central nervous systems during launch, during like the high accelerations of launch. Our experiment closely relates to NASA's torpor-inducing transfer habitats for humans for the mission to Mars. They're working on that right now. The pods are on the right there. We're hoping to kind of achieve a smaller scale on our model organisms. So our model organisms are Drosophila melanogaster, which is also known as the fruit fly. Their genome is homologous to over 60%. So they're pretty much what you find on a fruit fly is identical to humans by like over 60%. So they have extremely similar biological mechanisms and pathways that we can apply from fruit flies with this experiment to humans. The purpose and hypothesis of our experiment is we will be examining the behavior, oxygen intake, reaction time, and health of the insects before launch. So we will do a lot of control experiments on our flies and a lot of data acquisition about that during launch, which our sensors will read. And then after launch, we will do another examination on all of their mechanisms afterwards and behavior. We have a control group that will not be under therapeutic hypothermia. And then we have an experiment group that will be sedated under the low temperatures. We pretty much want to find out, will being in a hibernated state have a positive effect on the survivability and just the overall durability of the anatomy of the flies in a high stress environment. If the insects are launched under synthetic torpor, they will have a better chance of survival due to therapeutic hypothermia's protection of the cardiovascular system, the central nervous system, and overall anatomy, which is like muscles, wings, etc. That is our hypothesis. In order to find an adequate model organism for our experiment, we went through a trade study and we had upkeep. So it's pretty much how hard is it to take care of them? What experience do we have taking care of these insects? The accessibility, where can we buy them? How easy are they to get? How easy are they to re-up on? Our viability, which is like, at what points do they die? How long is their lifespan? How often do they mate? As well as like, what do they freeze under? What do they die under? And also like, if these bugs were to get out, a big thing we didn't want is like an invasive species of New Mexico. And then also the amount, which is just the amount that we can examine, put in the rocket, fit in the rocket, especially with like a smaller diameter, and flies won by a lot. So we do plan extensive documentation of our experiment just to ensure to everyone that we were doing it humanely, especially dealing with like living things. So we do have like fly upkeep documentation plans. We have a detailed upkeep procedure in our statement of work. All procedures and tasks are conducted in the fly lab that is on campus at UH, and they will be provided by the genetics professor. It'll also be logged in our upkeep journal, which it can also be seen in our drive. The instructions for fly upkeep will be created and further explained as we move closer to spring semester, just because we're focusing on onboarding new members for the concept of the experiment, and all of that will be charted out later on. So it's just a quick log just to make sure we're all on the same page, we communicate with each other, and we hope to check on them at least once a day, just because we want to make sure the viability of them, there's no infections, we can treat any infections, and then also just have extensive documentation and making sure our inventory is good. So Kevin will speak about the other elements of payload.
So for our housing design, our internal structure will have 3 different sections to it. So the top section, we plan on having a smaller enclosure that will have the control side of the experiment. We call it the Fly Control Containment Unit, the FCCU. Sadly, I don't have a CAD for it yet, so I'm sorry about that. The middle section of our payload will be for the electronics in the tray. And then the bottom section will be for our experiment, where the flies will be under the therapeutic hypothermia. The CADs on the right is our preliminary designs for the housing. So we'll have the flies within those vials, and then it'll go into the container, and then our cooling method will be within the container. And then for the lid for the vials, we plan on putting sensors on top along with cotton plugs so that they're able to breathe, and then everything will be secured properly once we assemble it. For our cooling system, we've looked into using an insulating case with a cold substance. One of the materials we plan on using is aerogel. Thank you, Alex, for donating aerogel to us. So we plan on using a cold substance to keep the insects within the temperature range we want. One of the other designs we've looked at is the cooling liquid pump. So this is the more active part of the cooling system. We're still not too sure about using a cooling liquid pump due to the complexities it would bring into our project, as well as the size limitation we have, and the requirement for having a pump and like all the tubing and stuff required for the liquid. So we plan on doing a cooling substance trade study. Some of the materials we've looked at are cooling gels, phase change materials, and ammonium nitrate and water, which is what we used last semester for our E. coli payload. And then we also have ice on our trade study. We're also working on a heat transfer calculator so that we can input material properties like the thermal conductivity, and we can adjust like the different layers, and then we'll see how the internal temperatures will be affected with our external temperature input. We've also talked to Dr. Gasemi for advice. So that's what we're working. He gave us the 1D transient heat conduction equation, which we're working on for our calculator. And he's also recommending us to use the phase change materials, which he thinks will work to reach our temperature range. So for our electronics, we'll be using the TNC 3.5 for our controller. And then for our infrared and visible light sensor, we'll be using the Adafruit LTR 329. This is mainly to get temperature and motion data from the insects. This sensor is about the size of like a quarter, so it should fit right on top of the vial, and it should have access to the flies. So yeah. And then our second sensor will be for the temperature, CO2, and humidity. This will just be within the payload bay. It'll be the Adafruit SCD 30 NDIR. As for future testing, we'll be doing thermal oven / heat chamber testing for our cooling system to make sure everything works properly next semester. We'll also be doing the therapeutic hypothermia tests and the control testing on the flies so that we have the before launch data to compare with our during and after data. We'll also be doing infrared testing with the flies to see what type of data we can get from it. And we'll also be doing more research into that as part of our design process. And then we'll be doing the vibrational effects testing for our motion sensors. We plan on doing that by launching the sensors within either our L1 or L2 rockets. Yeah, and then we also plan on developing additional tests as we progress through our design. So for our risk assessment, our first one will be the failing of the cooling system. We think it's likely to happen due to how hot it can get in New Mexico, and how likely we are able to completely seal the enclosure to keep all the cold air and stuff within the enclosure. The mitigation type will be design, and whenever mitigation approaches, we'll be using proper materials and sealants to prevent any leakage, of the cooling substances from the cooling enclosure. If it does fail, and depending how much it fails, how much leakage happens, or how much it can keep it cool, it could be catastrophic because it could prevent any of our experiment from happening. For our second hazard, we have vials housing the insects breaking. We think it's unlikely or seldom to break unless a lot of compressive force is put onto the vials, since the vials will be inside the enclosure. The mitigation type will be design, and then our mitigation approach will be choosing a vial with more durable materials. So we've been looking at the plastic containers that they use for medicine, like the little pill bottles. That's the type of materials we've looked at. And then we also have designing the enclosure to better secure the vial so it doesn't fall out and moves around within our payload too much. For our battery holder breaking or deforming, we think it's seldom to happen, since the materials we use will unlikely deform or have too much deformation from the high temperatures. Our mitigation type will be design, and then our approach will be choosing a more heat resistance and stronger mechanical properties for our materials. For our electronics overheating, we think it's likely to happen due to how hot it can get again. And if the electronics overheat too much, we won't be able to acquire any data for our experiment, so we think it would be catastrophic. Our mitigation type would be design, and we think proper placement of the sensors and choosing good materials for the holder will help mitigate this. As for our electrical fire hazard, we think it would seldom happen, since it would only happen if we use a liquid for our cooling system, and it's only if any leakage happens within our enclosure. The mitigation type would be design. We plan on mitigating this through designing our electronics section to have shielding from any possible leakage from the enclosure. Yeah.
So our following risks are that the battery overheats. The following causes are there. We have it likely to happen due to the high temperatures in New Mexico. It would be fairly catastrophic due to the data not being able to be acquired or not being viable. We plan to mitigate this through a design approach, just with proper placement of the battery and adequate material selection for the holder, which we are hoping for ABS. And after these mitigations, we rated this as medium. The insects dying is ranked high just because it is seldom to happen due to constant transport of the insects, but we're hoping by then we have enough handling experience that it will not happen. And it'll be catastrophic just because we cannot follow through with our experiment. We are doing a procedural approach to mitigate this. A guide/manual will be made to show all members how to properly handle and take care of the insects, and then proper maintenance of everything. So it should be low after our mitigations. Insect infection and injury is very seldom to happen. The injury is more likely than the infection, just because we have experience by then treating the infections. It's very minor because they can be treated for these things. We're just being very thorough on our risk assessment. We hope to mitigate this through our procedural steps, which is just proper sanitizing, making the food correctly, and then we can treat the infections with a combination of penicillin and streptomycin. So it should be a low risk after mitigation anyways. The insects escaping is seldom due to the material of the vials we have and the cotton plugs keeping them in, but it would be catastrophic just because we also could not go through with the experiment. But there is a design approach that we're taking. The lids have been designed to have a tight fit, and hopefully the vials are unbreakable or not easy to break. And then it should be low after those mitigations. Overcooling seems very seldom to happen due to the high temperatures in New Mexico. But we are aiming for around 50 degrees Fahrenheit at the coolest, or at the maximum temperature for our cooling system. And then the lowest temperature, we're aiming for above 32 degrees Fahrenheit. We're not trying to freeze them. We believe overcooling could happen just because depending on what cooling method we go with, It would be catastrophic just because if we freeze them too much, they could die. But we would choose a cooling substance that's not too cold. A reason that we looked into an active cooling system is just so in a perfect world, we would have an active cooling system that would turn on and off and regulate the temperature inside. But we ranked this low after our mitigations through design and procedure. For our budget, Payload was provided with $500. Everything with listed pricing are things that will come out of our budget. Everything with dashes are components that are provided for us, and everything in red is undecided on as we're still brainstorming through our cooling system.
So for our timeline, we'll mainly be focusing on finalizing our design and finishing the risk mitigation. So our next steps will be determining the cooling substances we'll be using, as well as the materials we'll be using for all the casings and installation. We plan on finishing our heat transfer calculations so we know if our design will work or not. And then we'll also be finalizing our payload housing design. And then, yeah, that's it.
Up next, we will have Christian and Bailey present about recovery.
Hey guys, my name's Christian and this is Bailey, and we are the recovery sub-team leads for this year. So we're going to start off with a brief recovery overview. So our goal in recovery for this year is to recover Shasta 6 in flight capable condition. We're going to do single bag dual deployment. For our drogue parachute, we're going with a high performance coefficient of drag 2.2, 36-inch chute. Going to get a descent rate of 120 feet per second and a snatch force of 74 based upon our calculators that we developed last year. Our primary CO2 and black powder systems will be our ejection systems. For main deployment, we're going to go with the Iris Ultra 72-inch, the exact same chute that was used on Zenith last year. Descent rate 25 feet per second, same as last year, and a snatch force of 193 pounds. In order to allow for single body dual deployment, we're going to use 2 L2 tender descenders in series for redundancy. So our ejection systems. Our primary this year is going to be the CO2 system. It's going to be the Raptor, uses 23-gram cartridges. The Raptor operates by using a small amount of black powder stored inside to move a charge piston. This charge piston punctures a CO2 canister, which then ejects CO2 into the recovery bay. This generates enough force to break 3 shear pins. 120 pounds is required to break these shear pins. So we set a value of 180, which is with a factor of safety of 1.5. The black powder system, it's operating based upon the high altitude centrifuge design we developed last year. So this basically uses black powder stored inside of a 4 milliliter centrifuge tube. It's packed tightly with ejection wadding and then sealed with vinyl tape. This provides back pressure for increased burn to make sure that the black powder sufficiently burns at higher altitudes, like 39,000 feet, which is our worst case scenario this year. That 2.07 grams is going to be needed to generate the separation force of 180 pounds. And again, in order to allow for single bag dual deployment, we're going to need tender descenders. We're going to use 2, again, for redundancy. They're heat-treated anodized aluminum. Set to 2,000 pounds of shock force being the maximum that they can take while still surviving, and a 500-pound maximum release weight. So in order to ensure that the middle quick links, as you can see in the middle between there, are recovered post-flight, we use a system of rubber bands attached to the inner and outer quick links. This ensures that in the event that both do go off, the middle quick links are not lost and are kept by both the main and the drogue sections as they are separated. And in order to ensure that we do not have any black powder burns, we're going to cover them with Nomex blanket. And here's a configuration of our shock cords for this year. So they're still a little bit subject to change, but as of now, the main lengths are going to be 20 for both main and drogue. So the first diagram off to the right there, that's our drogue deployment. The cord in red is going to be the length between the drogue and the tender descender. It's going to be 20 feet. 1/4 inch, 3,000-pound Kevlar. It's going to be the same for every length of shock cord except for the U-bolt to main, just because of the higher shock force that it's expected to take. For that, we're going to use 20 feet of 1/2 inch, 6,000-pound shock loop. The reason we're going to go with the shock loop is just to make sure that we don't have any issues with tying knots. The shock loops are much stronger than the Kevlar cords themselves and are stronger than any knot we could tie. So to minimize any issue with that, we're going to go with shock loops. And in order to retain the main bag, of course, we can't have that go flying off. We're going to use a 1 foot, 1/4 inch, 3,000-pound Kevlar shock cord length. All right, so last year we had a recovery issue with Zenith. We had one rubber bands that we used to attach the shock cords to the main bag, end up reefing the main chute inside of its deployment bag. This prevented main deployment, and instead we came down under drogue deployment at 120 feet per second or so. This is not ideal, obviously. In order to mitigate this, we've developed a number of techniques. First being daisy chaining. So this would replace the flaking that we do, which would minimize any issue with flaking in addition to the rubber bands. Ideally, this would allow us to remove the need for rubber bands at all around the main bag, thus eliminating the issues associated with the rubber bands. This method would absorb shock in much the same way as flaking does. As the cord is pulled in tension, shock force is transferred to allow the daisy chain to be broken and pulled into one single line. We've also come up with the idea of a shock lanyard. Well, more rather, with the help of Randy, we have come up with the idea of a shock lanyard. This would attach to all of the rubber bands attached onto the main bag and would ensure once the main bag is pulled in tension, the rubber bands either fall away or are broken entirely. Again, minimizing the risk associated with the rubber bands.
So moving on to parachutes, this year for a drogue, we have selected the 36-inch Rocketman Ultralight High Performance. It will have a coefficient of drag of 2.2, which we like because that's going to minimize our packing volume. As 8 gores, and this is a shape. If you would like me to pronounce it, I'm more than happy to, but as Christian can attest to, I will butcher it. It's like rural, but for rockets. It's going to have a weight of 3.1 ounces, and we're going to be right in the sweet spot of 1.2.83 feet per second. Our ideal descent rate would be 110 to 130 feet per second. And on Oberon and Zenith, we ended up having a descent rate of about 120. What this means is that we may have some slight discrepancies between our experimental value and our actual. But either way, we should be able to have the drogue in such a way that we will have a recoverable rocket. For our main, we once again have a coefficient of drag of 2.2, and we are going with the Rocketman 10-foot ultralight high performance. Once again, have this shape, laughing is encouraged, with a weight of 10.4 ounces. We have a descent rate of 24.37 feet per second. The one drawback to this is it is slightly outside of our ideal range. Oberon's was 22 feet per second, and Zenith's predicted was 25 feet per second. Going off of Zenith, we know that we have a slight margin of error to where we can safely recover that rocket. And so that is what we were planning on doing there. This is something that we wanted to talk to y'all about. So we are planning on going with the main, but there are some caveats. We have slight shroud line fraying in 2 areas. It is a single thread, but as you can see, there is some slight damage there. Within the parachute, which was our main concern, we have a quarter for reference, but there were 2 areas where there are some slight holes. They're very minor, and they are able to be repaired with ripstop nylon spinnaker tape. And now we move into SRAD parachute manufacturing. So this is something that our sub-team is very excited about for this upcoming year and is in large part due to Dom's generous contribution. So major round of applause to him for that. We are planning on developing SRAD parachutes for future competitions past Spaceport America Cup 2023. This will not only improve recovery's technical capabilities, but will allow us to have increased experience with the parachute manufacturing process. It's going to allow members to really get involved within our sub-team and kind of have a project that will make it their own. And it allows us to provide better documentation for Spaceport and for future parachute designs. It also allows us to have a greater understanding of factors that will affect parachute and recovery design. One of the major advantages to this is that SCR will now have parachutes that can be used for members when they're attaining their L1, L2, and L3 certifications. And we're also working with Hobby Rocketry to expand it over into that as well.
Gore design. We are currently ahead of schedule and it is still very much in the preliminary phases. So we are going to have this completed around early November, sometime before the CDR, but these are just the beginning stages. We are using a design program brought to you by Case Western, and we are going to be going with an elliptical design for the drogue. Right now, we've invested more effort into ripstop nylon, but we will be moving into Dacron because we will be running trade studies between the two. So we are going to want to have a design that is similar to Xena's drogue because that did prove very successful during launch. With SRAD, we are going to be lucky if we achieve a coefficient of drag around 1. With COTS parachutes, you're able to get a higher number, but that really isn't the case with SRAD, at least so far with the teams that we've talked to from Spaceport and with who we talked to at University of Minnesota. So right now we're looking at a 30-inch diameter for the drogue with a 4-inch spill hole. We're going to use nylon 550-pound paracord shroud lines to withstand shock force and size E. We've talked to University of Minnesota sub-team lead for recovery, and that is the type of size threading that they go with. It's been flight tested. We're going to continue with that trend. And it should come out to about 1.1 ounces. The annular design for the main will be completed after we have testing for both of our drogues. Stitching. So we currently have a decision matrix going on between the flat felled and French felled seams. We are leaning towards the French felled seams, but that's only going to be finalized once we finish completing once we conduct stress tests to determine how much the seams can handle. If it turns out that the flat felled seam can handle more, then that's going to be the one that we're going to go with. But right now it's looking like the French felled seams will. So the difference between the two. Flat felled seams are usually used when materials are less likely or are likely to experience stretching and stress. So you have seam allowances that are encased within the seam. They don't have any raw edges, and there's several rows of stitching to increase durability. French felled seams, which is why we like them, decrease the likelihood of fraying, and they're preferred for sheer, lightweight, and delicate fabrics, which is what we would be using for a parachute. They've also been flight tested with UMIN SRAD parachutes, so we know that they are going to be able to withstand flight because they have had many successful launches with them. And you need to finish the seam to strengthen it. So that's one drawback. It requires a little bit more work on our end, but once you do that, there are very few drawbacks to the stitch. Testing. So we're going to have coefficient drag and deployment time testing. We did this last year to verify the coefficient of drag, and it was the exact same number given to us by the manufacturer. So that's something that we know can be done and can be done very accurately. What we're going to be doing is we're going to be launching the parachutes off of Agnes Arnold's 5th floor with a 10-pound dumbbell, have a member film the entire frame or the entire descent, and then go and analyze the frames to determine how much time it takes the parachutes to fully open. And using the formula right there, we will be calculating descent velocity. And another theme. So basically for recovery, our general theme is going to be test, and more tests. We don't want to have any errors that we had like last year. And with SRAD, we know that there are a lot of things that can and will potentially go wrong. So we are doing everything in our power to minimize that, starting with L1 and L3 flight implementation testing. So as I previously mentioned, we're going to be working with Hobby Rocketry. That's going to give us more people that when they go for their L1, myself included, that we're going to be able to get data on that and to verify that the drogue parachutes do indeed work. Raj has generously agreed to test both our drogue and our main for his L3 test, which speaks to overall, especially that everyone's doing that, the team's confidence in our ability to fully pull this off. But it's great because that gives us more experience and a better understanding of how our parachutes are going to work in flight. Tensile strength testing, which I was also alluding to earlier. We're going to verify tensile strength for both our COTS shock cords and our SRAD parachute fabrics.
Alrighty, we also plan to conduct some ejection charge testing. So this is something we did extensively last year with the tinder descender, with the CD3 ejection system, the CO2, and the high altitude black powder system. We want to do the exact same thing again this year to validate the calculated amounts of CO2 and black powder sufficient for ejection based upon our calculator. So we're going to use the 23-gram CO2 cartridges with the Raptor and the 2.1 gram at current black powder charges for the sealed CO2, for the sealed centrifuge tubes. We also plan to conduct the shock cord rubber band brake testing. This is mainly to determine the force required to break rubber bands if we indeed do decide to go with the flaking method again. We also plan to test the lanyard device to see how well it pulls away and or breaks these rubber bands at the various forces that are required.
So for a risk assessment, as with any recovery system, you have a lot of things that can potentially go wrong. A lot of these are able to be mitigated by procedure, but as you see, we do have a lot. And so for the sake of succinctness, if y'all have any questions for this, we are more than happy to go over it. A lot of our hazards are such as black powder residue, are hazard to recovering components and people, burn damage to parachutes, premature ejection or TD misfire, complete ejection failure, CO2 system ejection failure, TD failure, main parachute failure. All these can be mitigated by procedure. So as long as we don't cut corners, as long as we are solid in everything that we're doing before we go to spaceport, as long as we drill it, because we know that once you get to spaceport, conditions are such to where it's like you're hot, you're tired, things may make mistakes. If you drill that, if we pay attention, if we're careful, we are going to be able to minimize those risks. Other things can be mitigated through design, such as main parachute from failed deployment method from bag. That's what happened last year with the rubber bands. We are going to be conducting testing so that we eliminate that possibility to the best of our ability. Other issues that can be mitigated by design include shock cord failure, not failure with the shock cords, tender center parts lost, and other factors pertaining to COTS, such as material failures, rips and tears, and component manufacturing defects are out of our control, but they still can be assessed. Just going over briefly once we receive everything and making sure that everything is properly in order.
Alrighty, so this year our recovery COTS budget is going to be $850. Majority of that so far is going to go to the new drogue parachute that we need, the coefficient of drag of 2.2 drogue, 3-foot diameter, as well as the new lengths of shock cord and the CO2 cartridges, which are not cheap, as we have discovered. The rest is going to be SRAD type materials, so anything from needles to thread to the ripstop nylon material itself. It's all going to be part of the SRAD budget. And timeline. So we have a number of tasks we must accomplish before reaching the CDR in November. We have to finalize shock cord lengths, determine the bulkhead placement and the U-bolt we're going to be using for the bulkhead. Determine testing to be done in spring. We have to get a full schedule done for that. We have to revisit the risk mitigation with the data we get from today. We have to continue to add materials to the BOM, finalize core designs for SRAD chutes, determine material choices, and finally, with any luck, begin drug manufacturing for the CDR. And that is it for recovery. Thank you.
And last of our sub teams is avionics with Raj and Sam.
Okay. Oh, okay.
Hi everyone, my name is Samantha Tobias Leja. I am a biomedical engineer major and I'm co-lead for avionics.
My name's Raj Gohil and I'm also the co-lead for avionics as well. So let's get started. So for avionics, our main goals and tasks this year are the same as always, but with regard to SRAD additions. So we will, as always, electronically detonate the recovery charges and collect telemetry data. We're making both a COTS and SRAD system with a portable ground station to view live data. We're going to provide critical information locating the recovery in the rocket this year. Our main goals is to transition to more SRAD components. So this year, 75% of our system is going to be SRAD. We're also going to work on improved geolocation systems, including but not limited to APRS tracking. So you can see here on here, the points in red are going to be the main things we're going to focus on improving this year. So just a brief overview how we divided avionics this year. We have two systems, the onboard flight computer system that's going to be inside the rocket and our grounded system that's going to be on the ground. So for our onboard system, we're going to have our COTS flight computer plus the structures of it. And we're also going to have the SRAD flight computer and the sensors as well. Our grounded system is mainly focused on the ground station plus software development. And we also have a mini team for telemetry, ham radio, and antenna development as well. So for our COTS primary flight computers this year, we selected the Telemetrum version 3. It's a dual deploy support flight computer with microsensors. It has onboard non-volatile memory with live data logging. So we'll be able to view the data live with an antenna. It has a barometric pressure sensor that works about to 100,000 feet, and it has an accelerometer and onboard GPS as well. To operate this, you need to have a ham radio license as it operates on a 70-centimeter ham radio band and uses a 3.7-volt LiPo battery. So we're going to encourage our avionics members to get their ham radio certifications, as we'll talk about later. And it's pretty lightweight, and it's about a really small size so that it can fit in about any rocket, even up to a size of 29 millimeters. And so as for our backup flight computer this year. It's going to be SCR's first SRAD flight computer that's going to actually electronically detonate charges. We've chosen the Teensy 4.1, and that has a pretty good CPU and RAM memory with a lot of digital pins and a lot of output pins. We chose this microcontroller due to its ease of use and also has an onboard SD card holder. So it's really easy to save data and data log. The sensors we chose for this flight computer, we're going to have a BMP 390 barometer, an accelerometer plus gyroscope, a BN0055 magnetometer, an ultimate GPS, and an XB Radio Pro 538 transceiver. So you can see here on the right, you can see our initial concept PCB boards starting to develop kind of like a flight computer PCB, especially for the Teensy. We're going to work really hard this year to even include terminal block outbreaks to include the ejection charges. So it's going to be a challenge, but we're prepared for it. So as for the structure and how we're going to place these flight computers, this year, instead of the tray layout like we've done in the past, we're going to do a combination of both a tray and horizontal stackable PCBs. So they're going to be mounted on 3D printed discs and standoffs with modular JSD port connections. So instead of soldering the wires directly and making them fixed, we're instead going to solder JSD ports and connect the wires that way for connections. This makes it easier to connect, and it also increases the chance of it not breaking apart once the rocket lands. We're also going to have a 3D printed tray on top of these horizontal PCBs to accommodate the COT system, terminals, and screw switches as well. So that way the telemetrum can stay fixed in a vertical position for flight mode. The advantages of having this mixed system this year is that it maximizes space in a 4-inch rocket. It also is really simple organization, as structures talked about earlier, and it has really easy wiring management. So on the right on that table, you can see on the bottom, we're going to have LiPo batteries that will be mounted onto the bulkhead through 3D printed brackets to holster them. On the first PCB horizontal, we're going to have the Teensy microcontroller. We're also going to have the SRAD ejection charge terminals. On the second PCB, we're going to have the sensors, so stuff like pressure sensors, accelerometers, magnetometers, and the gyroscope. And on the top, we're going to have our communications hub. So stuff like GPS and XB radios will be on that top PCB. And on the tray, we're going to have our COT systems as well.
So these are our 4 main sensors. So there's the barometer, the magnetometer, the accelerometer, the gyroscope, and the GPS breakout. So for the barometer is used for pressure and temperature, and atmospheric pressure is commonly used for weather measurement sensors. For our magnetometer is used for magnetic field intensity. And for accelerometer is used for acceleration, and the gyroscope is used for angular velocity in the X, Y, and Z axis. And our GPS breakout is used for location as well. And all of these 4 sensors are going to be part of our PCB, which I'm going to go ahead. Oh, and this is our ground station. It's focused on data collection of the sensors and the display of data from the flight computers. It uses an OLED display, and it uses altimeter to determine the data from apogee, acceleration, and velocity. We use the Arduino system program to calculate some of our data. This year, we're probably thinking of using Python to calculate instead of Arduino. So our COTS connection. So this year we were thinking of using 2 OLED displays. If you guys have any suggestions to what to use for our second 7-inch Raspberry Pi display. So for the first one is where we have altimeter, and it uses a 2G RAM. It uses 4 USB 2.0 ports, and it's a full-size HDMI port.
And so this year for our SRAD data collection software to collect our SRAD flight computer data, we're going to use a Raspberry Pi OS if possible with a Linux distro. And we're going to receive the SRAD sensor data from XB Radio. And basically how it works is that it will siphon the data to the Raspberry Pi, which will be connected to an XB Radio transceiver. And it's going to display all the software and the sensory data from the Teensy onto the display for the data acquisition software. As Sam mentioned earlier, we're looking to mainly using Python for this software, and we're going to be coding it from scratch. So we've been working really hard on doing that so far. We're going to talk about later more in depth about how the software is being programmed. But as you can see here on this picture, this is a general idea of how the software will be integrated into our Raspberry Pi system.
For our ground station PCBs, so we're gonna use a program called KiCad. We were probably thinking of using Ultimus or Eagle, but due to, us being college students, we can't really afford that. So KiCad has a feature that you can actually see a 3D printed version of your PCBs. So these are just some examples of PCB prototypes. Our main goal for our PCBs is to have modularity and also for future avionics system projects and leads to go ahead and reuse our PCB prototypes or to use it for inspiration as well.
So for our telemetry antenna setup this year, instead of one antenna like usual, we're going to use 3 antennas in conjunction with each other in order to have redundancy. So the first antenna we have is the usual Yagi antenna, which will be tuned to the telemetry version 3. It will be operating on 433 megahertz on a 70 centimeter band. The second antenna is for our SRAD system. We're going to be trying out a dipole antenna this year. It's going to be tuned to the XB Pro 538 radio. It's going to operate on 900 megahertz and on the 33 centimeter band. And finally, our last antenna is going to be an APRS Yagi antenna. And so the way this works is that it will be on a radio program where we'll hook it up to a ham radio, and we're going to track the rocket through a foxhunt style. So that way, which direction the Yagi is pointing, if it hears a beep in that direction, that's where we know the rocket's going to be. So it's kind of like playing a game of hot and cold and tracking the rocket that way. This year, we're having 3 methods, as last year we had a struggle when we lost telemetry and losing our GPS signal. So that's why we're trying to have as much redundant system as possible. And so to focus more on APRS and our ham radio collaboration, so this year we're going to use APRS as a ham radio feature. And this shares GPS location, temperature data up to 13 other data points over the air. And any ham radio operator in the vicinity with APRS acts as a repeater. And so at the spaceport launch site, there is an APRS capable radio station 17 miles west. And we will use APRS from the rocket to the radio station to track the rocket's trajectory and aid in its recovery. And that's why we're trying to encourage as many avionics members and members in SCR in general to get ham radio license so that they can help out in this.
Okay. Oh,
And so we also, another addition this year that we're going to try if time allots is an SRAD weather station. And so due to the unique desert environment in New Mexico, in the past, SCR has struggled with dealing with the environmental factors. Oftentimes we'll test here in like the Texas in normal weather. And then when we try our system at New Mexico, it just doesn't work simply because of heat or just the environment and elements are against us. So this year, if we time allots, we're going to try to build a weather station that collects weather data for analysis with other subteams, capstones, and research groups to analyze. So this can measure stuff like air quality, temperature, humidity, wind speed. We're going to think of utilizing an Arduino kit, but we're open to suggestions on how we could use this or build it. It's going to be a pretty simple but useful electronic project for avionics members to try to get to know. So it'll be pretty nice for us to have. And so future testing for us to have this year and to make sure our system performs nominally, we're going to have a heat testing of the tray and temperature measuring instruments to make sure they work and that the tray is pretty stable. We're also going to have pressure testing both the barometric sensors and the flight computers to make sure they correctly read altitude and that they perform normally. We're also going to have ground testing for activation of charges and in-depth continuity testing of wires to make sure that the system can properly ignite the charges. We're also going to have integration testing of the whole rocket plus the avionics system to make sure we can assemble it as easy as possible, and also telemetry range testing of the antennas to make sure that the connections are pretty nominal and that we can read data from faraway distances. And last but certainly not least, we're going to have flight testing of the SRAD flight computer on L2s. We're going to be doing pretty heavy testing on this SRAD flight computer as we know how tricky and scary it can be building something like this. So we're going to make sure it performs as normally as possible so that we don't run into any issues at spaceport.
So this is our second flight computer, Flight Sim. So one of our avionics members has had experience in building second flight computers. So as you can see on the dark screen, that's our source code, and then the actual simulation at the bottom. So with this, he injects fake sensory data into an SRAD flight computer and sees how the microcontroller reacts. This is very helpful because we get to see acceleration and other components of the rocket. It creates a 3D simulations to calculate expected position measurements and allows testing of flight computer on the ground. And for right now, Brandon is going to go ahead and talk about his second flight computer flight simulation. He's online right now. Brandon, can you hear us?
Yeah, can y'all hear me?
Mhm.
Okay, so I think with us with SCR moving towards a more SRAD point of view for as we get closer to Spaceport America, we wanted to develop a flight computer that was capable seamlessly as possible. So with the TNC 4.1, we were able to use all 8 of its serial channels, its 3 SPI channels, and its 2 I2C channels to break out pins if later on down the line we need to modify a flight computer based off of a certain flight profile. We could do that without having to change the fundamental architecture of the flight computer itself, which, as if anybody's made PCBs schedule. Along with that, there's a couple of redundant systems that we have planned for the initial prototype that we have in the works right now. One of which being analog circuitry to protect against inrush current, which can be a very big source of failure in case a component fails. We have protection against voltage spikes, which can also be very unpredictable. And another system that we were hoping to develop, microcontroller that communicates to the TNC, but not bidirectionally. With this system, we can have this second microcontroller read the TNC in cases that during flight, if the TNC fails for any reason, this second microcontroller can take control of the sensors and ensure that the rocket has a safe and high probability of deploying the parachutes, because if there's only one microcontroller, if that one microcontroller fails, there's no chance of parachute deployment and thus recovery. For ideas for the C3 or an ESP Room 32, both of which have Wi-Fi and Bluetooth and DSP now capabilities, which we can utilize on the ground to develop procedures that if we had a GUI on the ground, we can communicate with this second microcontroller to send commands.
That's enough. We got it, Brandon.
Send
The connection's like breaking up, but we got the
to
Brandon, se te está cortando. Brandon. Yes. Hold on, let me type it.
the main
Here, I got it.
Yeah, okay. I think.
All right.
No, don't
Oh,
mute him.
it's
Okay,
okay.
no, okay, I'll text him. Hold
Okay.
up.
Oh, you messaged him. Okay, bet. Okay. So our risk assessment for this year, the main ones we included are just, we selected our top 5, which are high source LiPo injuries, improper soldering or modification of the SRAM electronics, sensors returning bad data and messing up the algorithms, and improper handling of the ground station, and overall improper operation of the COTS or SRAM flight computers causing a misfire. So the main way we're going to try to mitigate these risks is mainly for procedures and design. So this year we're going to try to focus on training members on the proper use of telemetry and the LiPo batteries, designing electronics, and overall just try to develop safety procedures to operate these electronics. So you can see here, after we create all these mitigations, you can see our risks are either low or medium. So the main way we're going to try to mitigate all these risks is by proper training, proper procedures, and overall just safety of handling these electronics.
For our budget for avionics, they mentioned it was $1,000, and due to our LiPo batteries and our PCB boards with shipping and handling, our screw switches and our barometric sensors, some of our sensors won't be available until like next year. So we're taking a lot of precautions and a lot of research towards where to get the sensors. And especially if you bought like technology, shipping does cost like a lot. Most of our budget is really based on, of course, the sensors and we're actually gonna get new wire crimpers for space turbulence. Okay. All right, timeline. So we were thinking of having everything, most of the PCB board done by the end of November, or have most of it by the beginning of December, so we can start ordering and have testing on them. We continue to work on SRAC components and add-ons on the ground station for the rest of the month up to November 7th. And we determined to finalize new antenna setup by mid-November. We're doing a lot of research on that, and some of our members are actually in ham radio, so they're go ahead and working along with ham radio with this. To determine testing to be completed by spring, we are, of course, it's going to be mid-November, and critical design review will be mid-November as well. And
Yeah, that's a very
yeah.
Sorry about those technical difficulties. Thank you for bearing with us through that. Some of the final points we wanted to make before we open up for questions is Shasta's timeline for the spring. This is a little rough just because of we're mainly waiting on seeing how long components take to get in, and we all know the variability with that. But we plan to manufacture and spend most of our time manufacturing from January to February, and spend all of March testing, all of April practicing assembly, as Bailey brought up with a good point of getting through our procedures, nailing them down, making sure we know the ins and outs of our rocket, and we can assemble, I guess, in extreme conditions at spaceport as well. Throughout May, we'll have competition prep, so submitting all of those final documents, such as the technical report. And June, we will launch Shasta to 30,000 feet.
So this concludes our presentation. So we'll just be filling in some final points here and there. Just to reiterate, Shasta 6 is Space City Rocketry's second solid propellant 30K COTS rocket. The first one is the one that you see right in front of you to the right. That is Zenith. Most of the current leads took part in building Zenith and attended Spaceport. So this is the reason why we believe that this will be a successful year for us, because we will be able to learn from our past mistakes and ensure that we do not make the same one this year. We will be hosting the CDR next month, Friday, November 18th from 7 to 9 p.m. Our location has not yet been determined. And as I said, that concludes our presentation. You know, it was an extremely long presentation, so thank you for bearing with us. Also give a huge round of applause to Brandon for attending our presentation out of state. We will be hosting a 10-minute break before we start our questions, so you guys can go ahead and use the restroom and just relax before we start. So thank you so much. For those of you who are attending virtually, if you would like to start getting ready with your questions, you feel free to start typing them in the chat. Please and thank you.
Yes, and we also realize we're coming up on 9 p.m. So if you are needing to leave, we will be taking any further questions at our email, spacecityrocketry.uh@gmail.com. And we'll try to get back to you in a timely manner and respond to all of your inquiries. Thank you.
Alrighty, guys, we are getting ready to start the question portion of our presentation. So if I could get all of the leads to come up here, get ready. Thank you so much. Give a huge round of applause to all of our leads, guys, for all of their huge, amazing work. Okay, so we will be answering the in-person questions first. If you are still attending virtually, please raise your hand and we will do our best to get to you. If, however, for some reason we run out of time, we ask that you guys please send your questions to the email that you see right in front of you. So let's begin. Who has the first question? Emily, what is your question?
I'm just going to be repeating the questions just for recording's sake, just in case we can't hear. But Emily asked, what is your projected top speed?
So it varied slightly depending on which flight simulator we used, but worst case, Open Rocket predicted our highest, which is a max velo of a little over Mach 2, Mach 2.05, I think. Yeah.
Let's let's move on to the next question and then we'll get back to you. I promise. Okay, who has the next question? Alex.
So I know you guys are doing like a minimum time for rocket, but you're still buying like a commercial off-the-shelf airframe that's 4 inches, right? How much space is actually like in between the motor casing and that inner diameter of the airframe?
So Alex is
Like space at all?
Yes, Alex's question was confirming that we're still purchasing COTS airframes and asking for the space between the inner diameter of the airframe and the outer diameter of the motor casing. I believe the difference is 0.02 inches. 0.04, sorry. If we have, I have a picture I can show you of the airframe on the motor casing. If you're wondering if we can fit any structural components in that gap, there's very little space and we don't do that.
So then there's 0.02 inches of space basically all around.
Yeah.
Okay.
Yeah.
Are you guys worried at all that like that's going to, I don't know, vibrate at all in the rocket and it's going up, or you guys like have something that's like a spacer that's gonna go in there, or like something to like shim, or are you just gonna like fit it in there, assume it's gonna be fine?
Yeah. So the motor sleeve that we used for Zenith was the exact same material that we're planning on purchasing for the airframe. So just based on the fact that we didn't have any issues with vibrations or any movement inside of the motor case or the motor sleeve for Zenith, I don't expect any issues, especially because we'll be using the motor block and I guess torquing down some nuts to pull up on the motor casing. So no, I don't think we expect anything, but it's definitely something to look into, I guess.
all right. Next question, Gustavo.
What's the biggest challenge you think overall big space over the past?
Okay, a good question. So Gustavo's question was, what is the biggest challenge that we have faced thus far? Go ahead.
I think it'll be best to answer this kind of from a leads or a non-technical perspective, and then maybe also a technical answer. At least non-technically, I think the biggest challenge has been getting down our timeline correctly. It's been a huge challenge for Joe and I to show that we value, your health and your academics always come before the team, and we want to make sure those are in order and not ask all of our leads or our members to overextend themselves. But at the same time, you do need to make progress within the project. So coming up with an adequate timeline that can take both of those into account and also ensure that we're moving along the right track to launch at Spaceport next year has been probably the biggest challenge, at least for me. I don't know if any of you had a particular technical challenge you wanted to talk about. No, we're just that smart. No, I think technically, at least for me, I think has been deciding or looking into SRAD components, deciding how much are we actually going to integrate on Shasta versus regular COTS. Also, that decision to switch from 6 inches to 4 inches was not an easy one. Thank you for your support in that decision as well. But with that decision comes a lot of technical challenges, like increasing vertical space, then looking at buckling, now looking at different payload bay and avionics bay designs. How can all of our new systems configure to these new constraints that we have, especially considering a lot of aspects of our rocket are going to be things that we're trying for the first time and haven't been done before in SCR. So I hope that answers your question. I saw Randy, you had raised your hand online.
Yes. So I sent y'all, can you hear me?
Yes, we can hear you.
Okay, so I have 25 comments and questions that I sent to you by email. There's only 2 that I think are at the top of the list. One is on the modular fin can y'all are proposing. That's not going to work. And it's a short answer. You'll need to do a carbon, you need to bond the fins directly to the same airframe as the motor for the motor and do tip-to-tip carbon fiber. And as a caveat to that, it's not in this kind of design, the fillet is not materially important because it's used to transfer the forces from the surface of the fin to the surface of the airframe. So the fillet material is not important. If you're doing a tang through the airframe, then yeah, the fillets are very important, but 2 different things. The second one, I applaud your effort to go after an SRAD recovery system. It's a boatload of work, but when I just went online and checked the rules, the flight rules for SRAD electronics that are currently on ESRA's website, and this may change, I don't know, but it requires that for SRAD flight computers, you must be well documented and proof of function. This should include ground testing as well as flight testing before the competition. So my question or challenge y'all is, how are you going to flight test this thing with the current schedule that I heard proposed? I just don't see where y'all really have enough time to do it practically. But that's my observation. You know more about your schedule than I do.
So hi, Randy. This is Raj, the avionics co-lead. So
Yes.
I understand that like there's concern with documentation and just overall proving this function in such a short amount of time. One of the ways we are going to test this flight computer heavily is, like you said, through numerous ground testing. I talked about earlier how we have a flight sim program. We're going to numerously test that with the flight computer itself. So we're going to inject fake sensory data and see how it would act in real time as if it were flying. Also,
That's
yeah.
okay.
Yeah.
Raj, I understand what you're saying, and you're oh, by the way, don't use the word fake, it's simulated. Whenever you use fake, that creates the wrong impression in people, okay? Just an engineering word thing.
All right.
But even simulation is simulation. This
Yeah.
says flight testing, not simulated testing. So that's the challenge I see before you, is how you're going to procure the parts, fab it, get your app built for the SRAD flight computer, do your sims, but then how are you going to flight test it? And how are you going to get that done? And have you considered the risk whenever the rocket goes through Mach 1, if your and I've had this happen to me, where the flight computer mistakenly believes as you pass through Mach 1 that you've actually hit apogee, and it throws out your drove. And I've lost a rocket like that. And
Yes,
that was with a COTS altimeter that did me in on that one. So I don't ask. I'm not looking for answers. I'm merely asking you questions because you can't answer it off the cuff. But that's my big question: is how are you going to flight test this thing?
yeah, so we consider flight testing this thing a lot. This year, a lot of people are going for their L2s and L3s. So we're planning on testing that flight computer on
Who's
the,
going for L3s?
I'm going for an L3. There's a lot of
Do
members.
you have your taps?
Yeah, I'm actually contacting them at Spaceport as well.
No. Your taps with Tripoli.
Yeah.
So
I'll
Jarvis.
Yeah, I'm actually going out of state for my L3. Some other people are approving me for it. So
Cool.
So yeah,
Well, again, applaud your efforts there to get your L3.
Thank you.
That's great. It's also a boatload of work.
Hey, Randy, Brandon has some answers to your question. So Brandon,
Hi, Brandon.
Brandon, feel free to speak.
Hello. I'll try to keep this brief in case the mountains cancel my connection again.
Well, may I suggest that you kill the video? It's just so
Okay,
it's a
yeah.
voice that saves bandwidth.
Okay. So the prototype for the SRAD flight computer is already about, I would say, somewhere between 50 and 75% being done initially. Certainly there is some qualification testing that we'd have to do to make sure it can work in a controlled environment. And from data that we can and tuning that we can do from that allows us to have the confidence to launch on L1 rockets and L2 rockets. I don't try to go for certifications, but I have a couple rockets I could try to launch it on. There's a multitude of tests that we have written down already being planned for when we finish. So we should be able to get a certain degree of confidence from the SRAD flight computer from ground testing, but that is independent from flight testing. So regarding flight testing, I think the prototype, a working functional prototype can be done by the end of the semester, which gives us the winter break to work on documentation that isn't already done. I know there's some documentation that is already done, but if we can keep to that timeline, that gives us the entire spring semester to launch multiple of these SRAD flight computer prototypes on actual rockets to get confidence with actual flight testing and get real actual flight data that will be useful for Spaceport America Cup. Like I said, there is SITL functionality. It's actually almost done. I'm the one that's writing it. And that is a big part of the ground testing itself. But because it's a simulation and that's on the ground, you can only get so far with that before you actually need to get up in the air. But that is kind of internally what we're thinking of right now for the SRAD flight computer.
So let me ask you. So let me ask you.
But...
Yeah. So okay, fine. It sounds like you have plans, and that's good. You better check with the prefects at the launches that you want to use this thing, because as being prefect for Houston Tripoli, you can test fly it, but it cannot be the primary flight controller on any flight.
Yeah.
And the only last comment, because I don't want to take everybody's time up on this, is what are you going to do if you get to Spaceport America and they say you can't fly it? And that's all I'm going to ask. Other than that, y'all have a plan. You're going to work your plan. You're going to do your best to make it all work. And I really look forward to your success. But please make certain you stick to the rules rigidly.
Yeah,
Otherwise, those guys will ground you and y'all won't fly at all.
Yes, sir.
yeah, that's a really good point. So to my understanding, we have the rule book. So we have a pretty good understanding of the rules and regulations regarding avionics.
It's 6.10 SRED recovery electronics. I'm really good at quoting regs and rules. So now
Sounds like it.
I'm an engineer.
Gotcha. But yeah, we do have a copy of the rulebook, and so we're abiding by that throughout the design process. So to our understanding, by the time we get to Spaceport America, Kev, we'll have iterated enough to be compliant
You don't have to. You don't have to convince me. You have to convince the judges at Spaceport America. That's all I'm saying.
Brandon, I appreciate your input and thank you for answering the question.
Yeah, thank you, Brandon. Thank you, everybody. I really look forward to y'all's success with this. It'd be really cool.
Thank you. Yes, we just like to be able to cover as many questions as possible.
And that's why I said I'm done. Y'all can answer the rest of my questions later.
Yes, sir.
Thank you very much. Y'all have a great evening.
Thank you. Thank you.
Thank you.
Ciao. Bye.
Urban, in person.
Yeah, so I have a question for Brandon. So I understand that for the motor rotation system, you're gonna switch from aluminum to fiberglass, right? And you said that it would be easier to deal with that at the lab. Do you plan on like machining that yourself at the lab? I'm assuming it's gonna be a really thin cylinder. Is that gonna be a lot like that?
Urban's question was for Brandon and asking about the material of the motor retention system, asking about how fiberglass may necessarily be prepared in the lab as opposed to aluminum that we use for Zenith.
Yes, so the main reason I mentioned that is because especially with Zenith, we worked a lot with sanding fiberglass and shaping plates like that to, I guess, geometry that we need. So I'm sure you remember the quarter rings that we used for Zenith MLA. Thank you. I don't expect that we need to be able to work with, I guess, the cylinder that would be used for the motor block, because I think we are planning on getting that water cut or water jet cut or done elsewhere rather than the lab. But if we do need to make adjustments, like if there are any errors with that process, we need to sand it, change the geometry at all, drill holes through it. That would be really easily done with the tools that we have in the lab.
Car, actually, B, I believe you raised your hand before.
Yeah. So my first question would be both for payload and avionics, as both of you guys are dealing with electronics. What sort of validation do you guys have that these electronics are going to work under the amount of gravity forces that you guys are going to experience going up?
Okay, yeah. So hi V, this is Raj. So as for validating how these electronics will work, we're certainly going to see if maybe we could flight test them for these high G forces. Also, the reason why we selected these specific ones is because one, this specific light sensor would be pretty valuable, especially to vibrations, as stuff like motion sensors might be a little more inaccurate. So stuff like the light sensor, which can detect if there's IR light. So the way we're trying to use that sensor is that if it detects an increase or a huge amount of IR light, that means like the flies are awake. And if there's a low amount, that means the flies are not awake. So instead of just trying to measure the motion, we're going to determine our life signs through that sensor. And the CO2 sensor is the same deal. We're going to test that and see like if it's alive or not, the flies.
Okay, I'm so sorry. My internet completely cut out there. Was Raj able to give a reply to that? As soon as I don't know if you heard my full question, because as soon as I finished my question, it just froze up everything. I'm so sorry.
I'll have to ask you to refer back to the recording just so we can keep a steady pace of questions going.
No worries. Just wanted to make sure that my full question was heard and there was at least some understanding of that. Other than that, I also wanted to ask about the analysis. So I know analysis, it was mentioned earlier that they are recreating a flight sim software. So is there going to be any feature that is unique or distinctive about this design, or are you guys just recreating the wheel because you can? Like what is the advantage in this case to redesign it?
Yeah, so we actually haven't started that mainly because, well, one, it wasn't high on our priority list. But really the main reason is that Spaceport gives points for creativity and like SRAD wise. So we feel that this was really the only way analysis could do anything like SRAD related. So that was kind of the motivation behind that.
Okay. And then one last question, if I can. Okay, yeah. This one's for payload. You guys mentioned that the flies need to be kept within like a certain temperature control. I'm not sure if keeping like a specific temperature is like a goal of you guys, or you guys want to just keep within temperature range. But have you guys considered using PID and potentially looking into like a PID loop so you can have like an automated control system to regulate the heat inside?
We've thought about like an active system to control the temperature, but we're sort of shying away from that due to like our size restriction. The 4-inch diameter rocket will have like a lot less than that to work with. So we're trying to go with like a passive cooling system that will just keep the temperature within a certain range that we want. So yeah.
Okay, thank you.
And back to Emily and all of her wonderful questions.
PDR is pretty hard, but always that in the road, but you don't want that because you want something that's really pretty tested. So that's my first point I was going to bring up is you can't do that. Maybe as a tertiary, like a third system that they want it, but for your secondary, that's actually controlling much more hard to keep the bias. I had questions about your SRI computer though. First off, why do you have a magnetometer on it?
So the main reason why we kind of had a magnetometer. Oh, sorry. So the main reason why we added a magnetometer in the first place, it might be kind of silly, but we had a meeting. Well, the leads had a meeting with Randy, and one thing he brought about our altimeters is that they have a 10% error rate in detecting apogee, which can be pretty huge, especially when going to 30K. 10% is like 3,000 feet. So like we could have gone anywhere from like 27,000 to 33,000 feet and we wouldn't know. With a magnetometer, we're trying to mainly use that to data validate how high we went. So the way we would do that is the difference in magnetic field strength from at ground versus at 30,000 feet. And we would calculate that difference and seeing how high we went for that magnetometer.
Okay, so like that's very cool, but I don't know how precise that is. I mean, we need to talk to probably Dr. Baring about that. I mean, because if the Earth's magnetic field fluctuates daily, hourly, depending on the sun's activity, it changes position. So it's a dynamic system. It's not just like, oh, the magnetic field at this height indicates exactly. It's dynamic. So I don't know how strictly you can rely on that without doing a lot.
Yeah.
But I like that idea, and especially because it's magnetic Earth field, that's very exciting. But I don't know if it's going to be reliable for that.
All right.
Really excited though. So other question I had about that is you're talking about using Python for a ground system.
Yes, for SRAD ground station data collection software.
I'm not sure how I feel about that just because Python is kind of a slow language. And if you're having high extreme data, I think there could be other languages that could better suit for that task. Python is great for data analysis, doing that case, but for high speed computation, it's not. So something baser like C++ or even lower would probably work on a turn key.
Okay.
For this power.
All right.
APRS. You threw that out there, like you're going to use APRS, but that's kind of a whole big thing. You were talking about in hardware. I'm very curious about the antenna that you're taking on the rocket that's an APRS.
So Kurt, we're working with Kurt, the trustee of ham radio, and he's going to work with us to work on more on IPRS, like documentation for that. We're mainly going to be using like the telemetrum since it actually has an APRS capable chip on it. So we're mainly going to use that for APRS software. Last year we kind of did like I would say a bootleg version of APRS where we connected the Yagi to a ham radio. We tuned it to the same frequency as the telemetrum and then see where it would ping. Last year didn't work because obviously the battery cables ripped out due to the crash landing, but hypothetically speaking, we did test it in the lab and it does work. So we're trying to officially do that by actually going through a software. There's an online software, I'm not too sure what it's called specifically, Kurt knows, but it's basically you can go on there and let's say you're at home watching the Spaceport America Cup, you can actually log in and see where the rocket is right now straight from your home through Wi-Fi. So that's one way we're going to try to use that software.
Last question for Ethan. So I spoke to y'all before about the fact that you're that was happening.
Yeah.
The concern I raised to you back then was this flight computer has been through a big rocket crash. How are you going to ensure it's still performing nominally? What is your plan?
Yeah, so the main reason we're kind of iffy on that is budget, obviously. If we were to buy a whole new telemetrum, that's $300 automatically. So we're going to try and flight test the telemetrum. That's the very first thing. I'm not going to even let it go on Shasta without flight testing it personally. So we're going to try to do that. We're also going to pressure test it numerously as well. We did a pressure test as soon as we got back from the lab, and it did perform nominally. Like it read like all the correct altitudes, even if it did quick jumps in altitude, it read that pretty perfectly. So it seemed to be working in nominal condition. However, I know SCR has had that problem in the past where it seemed to be working. As soon as you put it on a rocket, it doesn't work. So we're going to try and test that, but that will be like a talk we'll have to have. Okay.
Alrighty, Carlos Soriano, what is your question?
Hello, everyone. Can you all hear me? Hopefully it's not too loud. First of all, great job, everyone. I'm really proud of y'all, and I wish I could be there. I do have a lot of questions, but I'm only going to ask one to give other people the opportunity to ask questions. By the way, Artis, he typed a question in chat during the break. So make sure you answer your question. But my question is for recovery. And this is just more like a safety concern because of what happened last year during the ground test when we destroyed the nose cone. For that, we use 180 pounds. And to me, that felt like it was just way too much force. And for Spaceport, we use 150 pounds. So I just wanted to make sure that whenever y'all do the ground test, you don't start off with the 2.5 grams, but instead like scale up to that point. And then the actual question was why single bay this year? I noticed that for some of the slides, they kind of just talked about the features, but there was not much justification of why those decisions were made. So not to pick on recovery, this is just something that I noticed throughout the presentation, but I just wanted to know why single bay this year compared to dual bay.
So overall, we decided to stick with single bay dual deployment because we've had experience with that on Zenith. We're confident in the tender descender's ability to work and for us to have a successful deployment, especially with conducting the rubber band testing to ensure that that doesn't happen again this year.
Does that suffice for an answer, Carlos?
Yes, thank you.
Okay, the question that was said in the chat. Hello, I am a member of the.
I'm still here actually.
Okay, perfect. Yes, go ahead and ask your question, please.
So I'm Gerhardus Lowhouse. I'm a member of the University of Louisville Spaceport America Cup team. I'm just watching this presentation. I too am also concerned about the fin can being separate from the rest of the body of the vehicle. Some of the detail I gave in the typed message was essentially that the motor casing inside of a tube of a vehicle is not a tight transition or interference fit. It's a clearance fit. So there's going to be the ability for that fin can to move relative to the rest of the body. And statically speaking, this is probably not a problem, except in the worst case scenarios of shortly after burnout, when the casing is no longer pressurized, the wall could buckle if there's significant moments, and that's also a very bad time to buckle your fin can. And then the second, probably more severe load case would be a ground impact. You might also buckle your casing, transmitting load through it because it's no longer pressurized. So I had questions like, is there a centering feature to align that fin can very accurately with the rest of the body? And have dynamics and flutter considerations been looked at for that assembly?
So that is a very good point about the, I guess, forces that would be exerted on the actual motor casing. Something that I definitely did not take into account, but that's definitely a very good point, and we will look into that. In terms of flutter and just the aerodynamic forces that would be exerted on the fin can, to my knowledge, I don't see any reason why it would differ majorly from, I guess, a more traditional route. But analysis might have some other thoughts about, I guess, the differences between a fin can assembly like the one we're kind of looking towards versus, I guess, a traditional manner.
Definitely, it would be hard to analyze. The dynamics are the most concerning part, and that's a hard problem to analyze. I would recommend that you make the fin can monolithic with the body unless there's a particularly compelling reason to keep it separate, because it introduces potentially quite a lot of programmatic risk for a structural failure shortly after burnout or at other times in flight. Because motor casings are fairly thin walled and they're great pressure vessels, but they're not very good at taking compressive loads, and they might dent. And a moment applied to the fin can or a lateral force would then manifest as a moment because you have a force couple. Those could fold or dent the motor casing, particularly after burnout when it's no longer internally pressurized. So that's just a recommendation. Secondarily, rail buttons. So option one, the rail button was stood off the outside of the vehicle, if I remember correctly. That considerably increases the moment arm available to break the rail button off of the body. Obviously, you can reinforce the rail button more in that case, so it just comes down to analysis which option is better. But have you considered using a rail guide? Those are kind of like a button, but they're stretched axially along the body, and they have a flange that wraps around the body that you could then, with a very large surface area, epoxy onto the body with appropriate surface prep, or potentially even put fabric over the flange.
I am not familiar with a rail guide. If you have any, I guess, like picture sources, anything like that you could, share with me so I could kind of be familiar with that, I'd love to take a look.
I may be able to, but if you just Google rail guide, you'll find all kinds of images from like Apogee Components and others. You'd probably want to make your own rail guide, so it's stronger than what's commercially available since it's a fairly large vehicle. But rail guides are a pretty common thing that you can just find with searching. And Randy seems to be experienced with rocketry, so he's probably seen them before as well.
Yeah. Okay. Thank you.
Thank you so much. Okay, anyone else have any questions? Yes, Alex. Yes.
Okay. So first, I guess I just want to bring up my biggest concern is you mentioned you want to epoxy like threaded inserts into these like bulkheads. What are the bulkheads going to be made out of? Just in fiberglass. Okay. I just I'm really skeptical about the idea of epoxy like threaded features into like to be like your fixation for like a threaded feature. I don't know. It's like it's just not a good idea. A lot can go wrong if you get epoxy in the threads, then it's all messed up. Since it's gonna be fiberglass, like I don't know the possibility of using steel coils for that, but if it were to be aluminum, I would totally suggest using steel coils. And I know you guys have tried that in the past and it hasn't like worked well, but like it's not, if you have the proper tooling and all that, like all the proper equipment, it can be done really easily. And I can help you guys out with that with like my company and stuff. They're just like, yeah, I would stay away from epoxy if possible. I know we've done that in the past, haven't we?
Yes, with Zenith.
It's just like, yeah, I don't know, it's risky. That's my biggest concern. The other thing, let's talk about the fiberglass rails.
Okay.
So like, how are you, like, how are you gonna fix these trays onto that exactly? 'Cause like, you can't like thread something onto it, right? It's just like, supposed to be like a rail system, like slide like trays on, right?
Yep.
So like, is it just gonna be some sort of friction fit type thing, or?
Okay. So in order to secure, I guess, are you talking about the avionics configuration for the?
Yeah.
Okay. So my thinking for, I'm actually going to so this would be a general idea of what the trays would look like for a configuration like this. Similar to, I'm sure you're familiar with the coupler design for the all-thread rods and how the tray is actually affixed in the center of that. I'm kind of thinking along the same route. So basically just designing the trays to be assembled in a way that once they are fully stacked and assembled on top of each other, as soon as we put the other bulkhead on top, that would sandwich everything together and basically keep the movement, I guess, vertically at a minimum.
Okay, so you'll still be able to like clamp on everything, keep in place.
Yes.
Okay, yeah, as long as you have that, that's good. I was just wondering, like, I wasn't sure how you do that. But as long as everything is like fixed and clamped in place, that works. Can you go back to the other slide? So I see in this like cross section, you have like the screw is like flush in there, and that's like the airframe, right? Like it's flush with the airframe.
Are you talking about the
Right
bay
there,
here?
so, like the head of the screw, like the socket head, is like all the way to the right?
Are you saying this portion?
Like the on the wall, like the left side. Yeah, right there.
Uh-huh.
So, like it goes all the way in, so like nothing is sticking out from the airframe.
Uh-huh.
Okay.
So are you saying that's the fastener or the threaded insert?
Well, I just want to like make sure, like I'm understanding it. Real quick, is that a cross section of the hole, or is that a fastener inside of it?
That is a cross section of the whole. Yeah, so there is no screw in this diagram.
Okay. It looks like a socket.
Yeah, it's just the threaded insert that would be epoxied inside. Yes.
Okay.
Yeah.
Can you look to the next slide?
Yeah, it's exactly the same thing.
Okay, yeah, I see it. Question on that section. Are those, I guess, long things that the screws are going into, are those the rails?
They are. And I realize the walls in this cross section look extremely thin. We would not be, expecting a wall thickness. 832. So yeah, so they could be machined. They could be bought. bought commercially in the sense that it would be a plate of fiberglass that we would then be able to cut and sand to the geometry that we need. So that's one of the reasons why I like utilizing the fiberglass, because we have a lot of experience with, cutting that, shaping that in the way that we need. So we would be able to buy it commercially and then just cut it to the size that we're looking for.
So at that point, I feel like honestly, it would be easier to buy like a commercial off the shelf, like smooth rock. It already has like threads in it. I'm sure you can find something like that on the Master, so you don't have to like, modify like a piece of fiberglass, cut it, and sand it, and all that. And like aluminum doesn't weigh much more than fiberglass.
So you're saying buy a product that would act like the rails that's already has threads inside?
Yeah, there is like these older kind of wheels that have threads already. Yeah.
Oh, okay. I know what you're talking about. Yeah.
So like that is essentially your rail. You don't have to like make like a custom fiberglass part.
Okay. That's a really interesting idea. I don't have any opposition to it. Yeah, for sure. And especially strength wise, which is one of the concerns that we do have with. Is that what you're gonna? Am I good to keep answering?
Thank you for your input, guys. So let's wait for us to raise our hands so that we can make sure that everyone is getting their questions answered. Thank you. Okay, Carlos. If you have a question, Carlos, you can go ahead and ask it now.
It was just a small little comment, but I think I can just like send a message later and somebody else can just ask.
Okay, that works. Gustavo, your question.
Also on structures, but moving away from the page, for the rail buttons, I know Brandon mentioned making some like new rail buttons made out of resin and molding it. My question is there any consideration with resin 3D printing?
Gustavo's question was, is there any consideration for a resin 3D printer? Okay, go ahead.
That is actually something that I thought about. I quickly dismissed it just because I don't believe we have access to a resin 3D printer, to my knowledge. But that would be a viable option. My only concern with that would be the strength of, I guess, the composition of that. I'm not super knowledgeable on the strength of resin 3D printed objects, but with the resin, I guess, molding techniques that we would use, we'd be able to, self-choose what resin we're using, what type of tensile strengths we're expecting, any type of material properties that we want to look for in those. But yes, I did think about it, but I did not kind of look farther into it.
Didn't Ozzy have one?
I don't know.
Don't they make composite resins with metal powders in it? So I know one of the two, I'm pretty sure it was Ozzy, got a resin printer at the end of last year. So they can even get something that has like metal powders in it. I don't remember looking at it.
Okay, well, I'd definitely be interested in reaching out and I guess the alumni chat just to see if anyone does have access to that. Okay, cool.
Okay, Haley, yes.
You can say after.
Oh, I'm so sorry, Brandon.
One, how are you going to calculate that if how flush are the prints that you'll be using to slot into those? Are they gonna have issues with epoxy kind of on the edges, like fillets on those parts, as well as the strength over time of constantly putting things in and out? I know we've had issues in the past with epoxy just kind of failing on us, just from constantly having things moving around, just move. And so I just worry if they're thin and there's just a dribble of epoxy down the side of it, is it just gonna eventually break on it, so they're gonna pulling things out at the reattach to the rail socket, so.
You want to read? Can I repeat the question? Okay, so the question was related to, let me see if I can go back. The epoxying of the rails, of these 4 rails in place on the internal diameter or internal radius of the coupler. So yes, that is something that I did consider when, I guess, going into the manufacturing of a coupler like this. I do expect there to be a slight radius of epoxy going from, I guess, the edge of the rail onto the radius of the coupler, to kind of get around that, because we are 3D printing, or have creative freedom in what these rails will look like. If it's not the the closest thing, but the section of the I guess the meeting point of the tray to the rail could have a slight chamfer on that edge to account for any imperfections of epoxy. I don't know if that makes sense. I might have to draw it out for you. Might be a little okay. But yeah, that is something I had to think about.
Thank you, Brandon. Okay,
I'm just gonna sit here for a second.
so we are getting to the end of our questions. So any last questions, and just make sure that you guys email them to us right here at spacyrocketry.uh@gmail.com. So our very final question, who will it be? I saw that Carlos also raised his hand. So. Emily, what is your question? Oh, a payload question. Okay.
So, like I told y'all, and I consider full experiment concepts of these. However, my concern is those flies happy and healthy in the chaos of Spaceport America. Not even when they're in the rocket, just like you're driving from Houston to New Mexico, you're taking a hotel, maybe an Airbnb, might be 5 people sitting in your bedroom with you, it's gonna be chaotic, and you're basically relying on cold packs that you have to constantly maintain to keep them cold, right? So I'm gonna bring in the question that strategy. I really think y'all need sort of refrigeration system, especially for in the rocket. Going now to the rocket, sorry for the long question, last one, but you guys know how long it takes to launch the rocket, even if you have it go, it may take you an hour to get it off the pad, your cold packs, the best cold pack on Earth, how long it's gonna last in the Mexican desert. So yeah, I would encourage y'all to have a more robust system than cold packs, and I was wondering if you guys have any ideas of how to ensure those flights are healthy and in the right temperature state.
Okay. Emily's question was, how are we going to make sure that the flies stay happy and healthy?
So outside of the rocket and the cooling experiment, the flies are kept at room temperature generally. They're very durable. They can survive up to like 130 degrees, and they can survive down to, you can freeze them for like a week and they'll be okay. I have a pretty good amount of experience handling these flies. I have like a 40-page paper I've written over research on them. So throughout transportation and things like that, we're coming up with a very thorough plan that will be documented in our statement of work about that. If we plan to cool them before going in the rocket, we make jokes about having a little hydro flask for them, but it might be the best plan, just to insulate them throughout the day. We don't yet have a plan for, I guess, when we get to spaceport, but they don't need to be refrigerated when we're there until like the day of launch. We do have experience with like being in the queue for 6 hours and stuff like that, which is why we're doing so much research into the cooling systems. I do want a more intricate cooling system. I think we have a lot of engineers that can do a lot of good work on that. But do you have any comments, Kevin? Like
I
that.
guess, I think one of the things we like want to implement maybe is like the like the uh liquid cooling system with like a pump and stuff. We're still looking into it. I know Izzy and Frankie really like that idea, but I'm not too sure how a pump and all the tubing and stuff we need would fit inside our payload bay. So we're still looking into it. I would like to have something more than just like a cold substance surrounding the insects, but that's just where we're at right now.
I just think like you guys have been so much work but then I feel like the opportunity that I would find a non-robust cooling system, right? So I really think that will keep the development.
Yeah, we're looking into an active cooling system. So there's I guess a pump that'll run through it. Depending on what substance will run through that. We looked into things like dry ice, just a coolant, anything like that. Dry ice would require like vent holes, which we can do. We just based off of like our time, or not time, but size restrictions and budget restrictions, we're still looking into that. Frankie is really betting on that, and I am too. And I just think it'll overall be better than just putting like ice in there and it melting throughout the day and stuff like that. So we're working really hard on doing that, and I expect big things from our cooling system.
Thank you so much. I am sorry, but that is all the time we have today for questions. Your questions are very important to us. So if you would like to get them answered, please email us at spacecityrocketry.uh@gmail.com. Thank you so much, guys. If you guys would like, I was thinking maybe we could set up a let us meet later on so that we can all get together and answer all of your questions at once. Does that sound good to you guys? All right, awesome. Expect a let us meet from me soon. Thank you so much. Round of applause to our lead, our beautiful lead. Y'all did amazing.